Hello everyone, my name is Christos and I'm a Senior Research Associate at GEOS Research and Innovation Center of Excellence. Today I will present a work that investigates supervised learning techniques to control active cameras with deep convolutional neural networks to go directly from visual information to camera movement. Active smart camera systems combine movable parts with onboard computer processing in order to provide extended coverage, flexibility, and cost efficiency compared to static vision cameras. Now, in many cases and applications of active camera systems, it's necessary to have real-time operation for resource-constrained hardware such as autonomous camera surveillance in mobile environments, mobile robots and drones, and intelligent interactive environments that can be set up on the spot and for temporary installation. An important operation of an active camera is to follow the targets in its field of view. The objective of active monitoring task is, in contrast to static camera setting, to change the control behavior of the camera in order to maximize the performance objective, such as keeping the targets in its field of view, in order to improve overall surveillance and monitoring capabilities. To achieve this task, we first need to obtain a displacement between the center mass of the targets and the camera image center. Then, using this displacement, we can direct the camera to follow the targets and keep them in the center of its field of view. We assume that the targets have equal importance and the goal is to try to monitor as many targets as possible. Traditionally, the active monitoring task has been handled through a pipeline of modules such as detection, filtering, tracking, and control, which is difficult to optimize jointly. In this paper, we frame the active visual monitoring task as an imitation learning problem. In this way, we mitigate all the complexity for optimization into the neural network. So we have a training approach that learns state action pairs, and during inference, the network, given a single image, can guide the camera to follow the targets in its field of view. We tackle this problem using behavioral cloning, which is an imitation learning approach focusing on learning the expert's policy using supervised learning. First, we collect demonstrations from an expert. Then we treat these demonstrations as independent state action pairs. And then we learn a policy using supervised learning by minimizing the loss between the predicted output and the output from the expert. Proper training and testing data are necessary to train a deep CNN regressor for the visual active monitoring task. For this reason, a framework is developed that allows for simulating the behavior of active cameras using real-world images, capturing and storing multiple frame sequences with ground truth data that can be used for bounding box, regression, density estimation, and camera control, and also to evaluate the performance of different algorithms in a realistic environment, in similar conditions, and in controlled experiments. Even though we're working in a simulation environment and moving the camera in a virtual way using image coordinates, this can be directly translated into actual camera motions of a servo motor by associating the image dimensions and the displacement in pixels with the camera field of view in angles. In this way, we can directly move the approach into a real-world setting without having to modify any of the previous assumptions. Since there is no dataset dedicated for the task of active monitoring, we develop a custom dataset. We utilize the PETS 2009 dataset since it has high resolution frames that we can use as the environment where we can navigate inside the larger frame, a virtual active camera. We have a dataset of over 3,000 images split into training and testing. And furthermore, we have also a different set for video frames that can be used for testing as well as additional images. To capture each frame, we generate smaller crops from the larger images, and for each of the small crops, we find the number of targets, which is given from the ground truth bounding box annotations, and compute ground truth displacement in the X and Y direction. Now, this results in imbalanced datasets where most of the motion are mostly in the central image regions. In order to make the network learn larger motions, we perform undersampling in the small motion region and oversampling in the larger motion region. The active camera deep controller network was designed to be computationally efficient. We employ downsampling early in the network to reduce the feature size. We use a small kernel size of 3 by 3, and we employ small number of filters in the early layers where their image resolution is still high. Further, it's comprised of two main subnetworks: the convolutional feature extractor, the layers of which were designed to perform feature extraction. We use 7 major blocks, each comprised of a convolutional layer with leaky ReLU and batch normalization. Further, we employ a controller subnetwork. The controller subnetwork is comprised of both convolutional as well as fully connected layers. The idea behind this is that the convolutional layers will condense the information from the feature extractor. Then the final convolution in the fully connected layers will convert the feature map into an actionable vector. Overall, the network has around 386,000 parameters, which result in a small network requiring around 4 megabytes. So the lightweight network structure allows it to run even on low-end CPUs. The output of the controller subnetwork is further processed through a clipped linear activation that bounds the output between -1 and 1, and this is done to estimate the motion of the horizontal and vertical direction with respect to the image coordinates. And the third output neuron that regresses the number of targets uses a ReLU activation in order to discard negative numbers. For the loss function, we employ the mean squared error to regress the count of targets, and for the motion in the x and y direction, we employ the absolute error. These were found empirically to perform slightly better than mean square error for the motion vector. For training, we implement the approach in TensorFlow and Keras on a computer with a Titan Xp GPU with an i7 processor and 32 gigabytes of RAM. We use the Adam optimization method for estimating the updated value of the weights. We use a learning rate of 0.001, and we decrease it by a factor of 0.005 every 5 epochs. We train the CNN for 500 epochs with a batch size of 32. For comparison purposes, we use methods commonly used to develop active monitoring pipelines, such as SVM person detector that is available in OpenCV and commonly used in low-power applications. We also employ the YOLO detection network that is based on a convolutional single-shot detection network, and for both cases, we also employ a tracking approach using the Kalman filter and the Hungarian algorithm for bounding box association. In addition, we also compare with an Oracle approach that has all the ground truth information of the bounding boxes and is able to find for each frame the best motion of the camera. The first experiments involved using still images. As you see on the right, this involves feeding each approach with an input image, and we display the number of targets in the image that is evaluated by each of the approaches, as well as an arrow indicating the direction of motion for each frame. We measure the error of each approach with regards to the two motion components and the target count compared to the Oracle ground truth approach. As we can see, the proposed CNN regressor approach manages to provide the lowest errors across all of these three quantities. Now we move our attention to image sequences. In this series of experiments, we want to monitor how many targets have been monitored by each approach. As we can see, the Oracle approach with ground truth information follows on average 3 targets in each frame. The tracking components for both YOLO and SVM detectors manage to increase the performance of each respective detection method, and the effect of which is not observed in this previous experiment. The proposed CNN regressor manages to beat the other methods and be close to the Oracle. By observing the results, we can see that the worst performance of YOLO and SVM can be attributed to their over-reliance on bounding boxes, where missing detections and inaccurate localizations can lead to inaccurate control. Finally, it is worth noting that the proposed approach, when evaluated on a CPU, can still provide adequate frames per second, making it an adequate approach for real-time surveillance applications. We visualize the feature maps extracted from the feature extraction subnetwork during both the training and inference phase. We do this by averaging channel-wise and upsampling to the image dimensions. First of all, this gives us a clear indication that the network tries to learn and focus on regions of people to make its decision on the control output, and we see that both in the training and the inference phase. We also see that the network during training learns to focus first on small targets and then move its attention into larger targets. It is interesting that the network is never given the bounding boxes and never explicitly trained to detect people or any other body part, but learns to do that automatically and focus on the correct regions. It is also important to note that this information extracted by the network itself can be utilized to provide weak localization information and bounding region information for the visible targets. Let's see now some demonstrations on video sequences. In these experiments, the network is given a frame by frame for each video and decides for each frame the best action to move. Note that there is no sharing between the video frames and no information is exchanged over time. The blue line will demonstrate the action that the network wants to perform and the motion that it will carry out. At the same time, the network will also display the amount of targets that is regressed and estimated. Notice and see how this number changes as targets enter and leave the field of view. In the first video, we see the capability of the network to follow large groups of people and at the same time estimate their density with considerable accuracy. In the second video, we see how the network manages to choose between two targets moving in opposite directions and then follow a large group of people. In the third video, we see that the network is able to keep up with targets that cover its whole horizontal field of view. In the last video, we see how the network navigates a scene where people are present everywhere in its field of view. And perhaps this also highlights some existing limitations. As people move, it tries to reposition itself, and as a result, it keeps moving around. This also highlights the limitations of the simulation environment, as the network reaches the boundaries of the larger frame and cannot move further outside the frame. It is evident, though, that the network is able to attend to the targets even in challenging conditions. So in summary, the objective of this work was to investigate how we can go from visual information to camera movement in order to be able to avoid decomposing the problem of active visual monitoring into the various subcomponents and try and see if an end-to-end system can optimize all these processing steps simultaneously. We have shown how to formulate the problem to be solved in end-to-end manner by deep learning, using existing datasets and repurposing them for this task. We have shown how we can develop a CNN tailored for the active monitoring task, suitable for smart cameras to do this lightweight construction. Overall, we show that this approach manages to provide a less complex paradigm with reduced computational costs that can be used in future smart camera systems. Currently, work focuses on building a real experimental setup through which we can evaluate the approach and how it can be used to guide real pan-tilt cameras. Initial results show that the approach indeed transfers well to certain conditions and is able to make the camera follow targets in unseen conditions. Also, our approach in the future is to robustify the network by incorporating temporal information so that the network can better account for the motion patterns of targets. You can find more details and results in the paper. Thank you very much for your attention, and please don't hesitate to reach me in case of any inquiries and questions. Thank you.